I guess I will start. Well, my name is Naomi, and I will talk about why do we need another time serial database. Let me just check if everything's okay. It seems fine. Okay. So why do we need another time serial database? Well, who am I? My pronouns are she and her. I'm a tools engineer at Course One, hobbyist game developer, mostly a writer, so I have 3 books published. I'm currently working with open source Rust and at tools at Chorus One. I'm creator and maintainer of BuriDB, Transistor, EDNRS, Beercode, Transfixer, and Rust Hiccup. My GitHub and Twitter are Naomi. So what is a database? Databases are a set of organized data that through some kind of relation generate a sense of meaning to this data. So they are generally separated between SQL and NoSQL, but that's just the tip of the iceberg. They can be property relations, time relation, if data needs to be reusable, graph, and many more. So how data is organized defines which kind of database you are using. So SQL, NoSQL, and whatever more. Whatever more we will see later, but SQL data is determined by relational algebra between the data in the database. NoSQL usually refers to non-relational algebra. So graph databases, document databases, key value databases, and there's a special kind of database called NoSQL time serial database that is usually a NoSQL database. That data is mainly registered in events over time. So this is a small example of how many kinds of databases we have, and some of them have databases that can do both two things, can do many different things. So we have graph databases, document databases, key value. They are mainly NoSQL. We have new SQL databases. We have the regular SQL databases. There's just relational algebra. We have big tables, and some of them can have more than one of these definitions. So for databases, one thing is very important, is the cap theorem. So you have to choose between 2 of these properties. So consistency, availability, and partition. So consistency means that all clients see the same data at the same time. By availability, the system continues to operate even if if there is presence of failure in the node, and partition tolerance is the system can operate in spite of network problems. So, but this is not really true, because most databases can't really have both. Can't really have 2 of them at the same time, but they get really close to it. So my database is mainly consistent. So, but not all databases are right for you. You have to choose them wisely. There are so many paradigms, and the paradigms need to be adapted to your data. So this is really important. What's the purpose of a time serial database then? Time serial databases have 2 main purposes: is to audit data, as all events from an entity have been registered over time. It's easy to identify inconsistencies in the data, and another purpose is to travel in time. So it's really easy to travel, and you can see how was your data in the time range that you are interested. And some of these time serial databases have relational capabilities, and these relational capabilities can be used over time. So this is really interesting. So because you can compare data over time. So here I bring the four main time series databases that I have worked with. Prometheus is a database used mostly for event monitoring and alert, as it records metrics in real time in a time series order. InfluxDB is a fast and high availability time series storage. It is mainly used for monitoring metrics, sensor data, and real-time analytics. And the last two are the more interesting databases for general purpose usage. So CruxDB is a bitemporal, which means you have the transaction time and the valid time. While the transaction time cannot be changed, the valid time can be changed. So you can fix time errors in your database. It's key value, and it's a graph query database that uses Datalog to support this graph query. So you can search over data with Datalog, and it supports different backends. While Datomic is a transactional time series database with rich queries over Datalog, its most famous usage is Nubank in Brazil, and it has relational capabilities. So these four databases are the main inspiration for my time series database that's called WuriDB. And why did I develop a new database, this one called WuriDB? So Datomic and Crux are very strictly related to closure environment, although for Crux there is two clients, Transistor and Translixer, that support Rust and Elixir. Datomic depends mainly on DynamoDB, so it's not even a standalone database. CruxDB depends on the chosen backend, so you can have Kafka, you can have Dynamo, you can have many databases. Influx and Prometheus are mainly metrics-oriented, and I wanted to prove that Rust was a good choice for developing a database. So Rust has a small memory footprint, which means that this database will get a good performance with a small memory footprint, and it's really safe. So I have safety over accessing data, which helps me to efficiently write and read from files. Also, WuriDB is a self-contained database with HTTP support, so all data can be queried through HTTP. This is the repository. It's currently on beta 8 version. It's mainly Rust, and it has a few contributors already. So this is the book that I've written to help people use WuriDB. It's an experimental general purpose time series database. Its name comes from Korean, from hour in Korean, and the project inspirations were those four databases that I talked in the past: SparkQL and Datalog for the query language that I called the WQL, and a few books written here. So how does WuriDB work? It has a list of features. So it's mainly inspired by my usage of Datomic at Nubank. So the query language is inspired by SparkQL and Datalog. It's really similar to SparkQL, but has some Datalog syntax in it. It's time serial. Its main purpose is to be time serial. It's schemaless, so you can send any kind of data you like, and it will adapt to the data it already has. It has deep key value storage, So you can have maps inside of maps. It has HTTP support, authentication, authorization, and encryption of the data. It does support very large numbers. So beyond you integer 128 in Rust, it has a conditional update that I will explain later. It has file compression with ZSTD. It's fast, and it has support for querying an entity history. So you can go back in time and query a range of the entity history, and it does support basic relation of algebra, basic. So having an idea, it's important to have an idea of how big your machine to support WordDB needs to be. So if you have around 100,000 entries a day, your file size can reach between 6 and 9 gigabytes. They will be compressed every 7 days, which is configurable to less, but usually 7 days is okay, and they will be reduced to 12 or 35% of their size, depending on how the data has been organized while inserting. One important consideration is stack and heap memory consumptions for 100,000 entities can go up to 10 gigabytes. As it uses the B-tree map, it's log n. So if you have 1 million entities, will not be 100 gigabytes, will be like 20% more. So this is important for the next slide. To some architectural considerations while you're using WordDB. So WordDB is fast, but it supports very large queries, and so it has it has more or less the same performance for large queries and small queries. So really small queries take around 3 microseconds, and like querying 1 million entities take around 7 microseconds if no other data is being queried. Queries read data, so there is a query endpoint, transaction insert and update data. So there is a transaction endpoint. Entity history, to query the history, has its own endpoint, and it's triggerable by a feature. So you need to say you want to have this supported. Encrypted data cannot be queried, so it cannot be read, but it can be checked. I will explain this later. You should keep one database per service, as it's cheaper this way, and sharding the database, it's a good idea when you have a lot of customers. WordDB is not naturally distributed, so this can become a problem if you need this partition. WordDB is internally async and based on nectars. It has one worker to guarantee consistency, and the trade-off of having only one worker is that it supports multiple cores to parallelize data processing. So it's faster this way than having two cores, two workers. So a few transaction examples. If you want to create an entity, just say create entity and the name. If you want to have unique entities, you use the keyword unique and a set with the unique entities. If you want to encrypt one entity, you use the keyword encrypt and the set of these keywords that you want to encrypt. Insert is really simple. There are two kinds of updates here. So update set and update content. Update set resets resets the content saved in the entity. So if you have in the database 4, A equals 4 and B equals 0, it will be reset to A equals -4 and B equals 32. And update contents will do some arithmetic over the data. So if A is 30 and you say that the new update A is minus 34, you will have minus 4 as a result. And here you have the match update as a conditional. If all conditions here are matched, it will update as a set. So it will reset the data. And there is delete and evict. Delete deletes the last update for the entity, while evict deletes the whole entity from the database. You can delete an entity table or the whole entity. So an example response, it's usually wrong, but it does have JSON support, and the state is returned in a simple manner that can be queried with the client. So query check is how we can check for encrypted data. So we send check the keyword that we want and the phrase that we want to check to the entity. If the response is true, it will send us true. And if it's false, it will send us false. If you try to check a non-encrypted data, it will throw an error saying that this data cannot be checked because it's not encrypted. So query selects, we have select all. That's just like SQL. We can query a few keys from the entity. We can query a few keys in specific IDs. Select the select with the keyword ID, similar to select where ID equals this. All IDs are UUIDs. We can query in a specific time. So this takes a little longer than just querying a specific times takes a little longer than query all data, because it needs to run through files. And you can query in a time range as well as you can query with a where. So it does support relational algebra. So you have group by, where the query response will be grouped by the key that you have sent that you want to group by. You can order data, so it will be ordered by key. You can deduct data, so it will remove data that have the same key. You can limit, so if you want to have only 10 entities, you will get 10 entities, and you can offset by an integer. You do have count, so you can get how many elements you have. You do have unions. Unions, they unite two different entities into one response by a query, which is different than join in here. Intersects, you will intersect two entities, so you are not intersecting the whole domain of the table. You're just intersecting two entities. As the same for difference, you have the difference between two entities, what is different in them, and you can join. Then you join two queries by a key. So you say you want to join all queries by key A, and it will join both queries by key A. You do have entity support, so it's a curl here, example of how to send a response, and you will have like the entity, the time it was changed, and the state it has with the transaction time. So for all of them, you will have this. And a request for entity history. is the entity key, the ID you want, start time and end time are optional. And thank you. I won't say that do it, even if people tell you it's too hard or you can't do it, at least you should try. So that's all.